Okay, so let's have Dr. Bhardwaj from Oxford, and he will talk about non-invertible symmetries and higher categories.
So let me begin by thanking the organizers for giving me an opportunity to speak here. I'll be talking about non-invertible symmetries in quantum field theory and their relationship to higher categories. So let me begin by saying a few words about the physics of the problem that we are interested in. So we want to study global symmetries in quantum field theory. And the reason we are interested in them is because they are powerful tools for probing strong coupling phenomena in quantum field theory. So once you know about the global symmetries, you can use them to learn about physics at any energy scales. And this includes energy scales where the physics might be strongly coupled and hence intractable to perturbation theory. So one scenario is in the infrared at very low energies, where these global symmetries provide insight into the phase structure of the quantum field theory and provide non-trivial information like confinement, etc. And this kind of application of global symmetries is typically useful in spacetime dimension less than or equal to 4, because it's in this spacetime dimension that we have interesting examples of quantum field theories which are strongly coupled in the infrared. So in the last decade, there has been a lot of effort done to explore this application of global symmetries for various kinds of global symmetries and generalized global symmetries by various groups of people mentioned over here. Now, another kind of application that you can consider is in the ultraviolet, which is at extremely high energies, or equivalently at extremely short distances, about the microscopic structure of the theory. And here, global symmetries provide insight into the spectrum and properties of various kinds of operators in the theory. These can be topological or non-topological operators and of various dimensions. So this can be point-like local operators or extended operators that can be placed along various submanifolds of spacetime. And these kind of applications are typically useful in spacetime dimension greater than or equal to 4. Because there exist interesting examples of quantum field theories which are strongly coupled in the ultraviolet in these higher dimensions. So they are a little bit complementary to each other, these kind of applications. About these ultraviolet applications, there has been a lot of effort done in the last couple of years by many people mentioned over here, which exploring and computing various kinds of symmetries of higher dimensional quantum field theories. So what are global symmetries? Well, the modern point of view is that global symmetries correspond to topological defect operators in the theory. So a standard global symmetry that we are used to corresponds to topological codimension 1 defects. And the group, the global symmetry group, describes the fusion rule of these defects. So in this talk, all the capital Ds will denote topological defects, and the subscript will denote the dimension of it. So since we have codimension 1, the subscript is D-1 over here. And the superscript will denote various different types of topological defects having the same dimension. So now this can be generalized to P-form global symmetry groups, where instead of having codimension 1 defects, you have codimension P+1 defects, and the fusion rule is controlled by the group. And now moving on to non-invertible symmetries, what happens over here is that you don't have a group law anymore, but you instead have a ring structure, which is known as a fusion ring. So here in this scenario, we have 2 codimension P+1 topological defects, say the A and B defects. And when you fuse them together, you obtain, in general, a sum of various codimension P+1 topological defects. So there has been a lot of recent activity in the last 1 year trying to find examples of such kind of non-invertible symmetries and understanding the properties in theories of space-time dimension bigger than 3. And these are some of the works which take this job. But for the purposes of this talk, there are more information inside non-invertible symmetries that we want to explore. So if you think abstractly about topological defects in quantum field theory, you realize that they should form a D-1 category. So how does this work? So you have objects in this category correspond to topological defects, codimension 1 defects in the theory. And then 1 morphisms between these objects correspond to codimension 2 topological junctions between codimension 1 topological defects. So here there are 2 1 morphisms shown over here in 2 different kinds of blue. And then 2 morphisms correspond to codimension 3 topological junctions between codimension 2 topological junctions. One example is shown over here in red. And then you can keep going on. You can look at higher morphisms which correspond to higher codimension topological junctions. So we expect this D-1 category structure, and we also expect a fusion ring. So at least we expect a fusion D-1 category describing the symmetries of a quantum field theory. Now on top of this, there can be various other structures, some braiding structures which depend on the dimension of the space-time. So that's what we want to study. We want to study fusion higher categories, but this is a hard subject. First of all, it's hard to even define what a fusion higher category is. So it's hard to provide a list of axioms that such categories need to satisfy. And already for fusion 2 categories, this was done only very recently. And then suppose you have such a list of axioms, it's hard to provide concrete examples which will satisfy these axioms. So it's hard to come up with examples, and it's hard to check that these axioms are satisfied. So in this talk, I'm going to take a more pragmatic hands-on approach and study the higher categories arising from studying symmetries of quantum field theory. And so I won't be providing a list of axioms that they need to satisfy, but all of the information about these higher categories can be computed explicitly. So they are examples of whatever the right structure there is to describe the symmetries. And the proposal takes the form, so morally, what we are going to do is we are going to start with some very simple higher categories. So take some higher form symmetry group. It's a very trivial higher category. And then you also have an action of G, some finite group on it. And then we are going to equivariantize this higher category with respect to this G action. And this equivariantization process will convert something trivial into a non-trivial higher category. So physically what's going on is that we have some theory with higher form symmetries. And we also have a zero form symmetry which can act on higher form symmetries. And then we are going to gauge this zero form symmetry to go to a new theory and ask, what is the symmetry category for this new theory obtained after gauging? To get into this equivariantization procedure that I want to describe, let me begin with the case which is very well understood, which is the case of one category to begin with. And before going into the general detail, let me first begin with an example where the rules of equivariantization will be physically explained and motivated, which we can then generalize. And in this example, we will go from one category describing invertible symmetries to one category describing non-invertible symmetries. So the physical theory that we begin with is a three-dimensional theory. It's a pure gauge theory. So it has gauge fields, but no matter content. And the gauge group is taken to be spin 4n. So this gauge group has a center Z2 times Z2, which becomes the one-form symmetry of this theory. And this one-form symmetry in 3 dimensions corresponds to topological line operators. By the arguments that I discussed on the previous slide, topological line operators are expected to form a 1 category. So there is a 1 category that we can associate to this symmetry in the spin 4n theory. Let's call it spin C spin 4n. And its objects are given simply by the elements of Z2 times Z2. So here we have the identity object, and then we have 3 Z2 generators labeled by S, C, and V. And the labeling reflects the fact that they're related to irreducible representations of spin 4n. Namely spinner, co-spinner, and vector representations. Also, we have a zero-form symmetry in this theory, which can be thought of as the charge conjugation symmetry. It arises from the outer automorphism of the gauge group spin 4n, and it exchanges the spinner and co-spinner. So it acts on these one-form symmetries by exchanging these lines D1S and D1C. So now we want to gauge this outer automorphism symmetry. So we get a new extra Z2 factor in the gauge group. So our gauge group is spin 4n, and the Z2 acts on spin 4n. So we obtain a semi-direct product. And this can be recognized as the pin plus 4n gauge group. So now after gauging, we are studying a 3-dimensional pure pin plus 4n gauge theory. And we want to know what is the 1 category formed by topological lines and local operators in this theory. Okay, so to understand this, let's begin with the topological lines in the spin theory and see what happens to them under this gauging procedure. So first of all, note that the spinner and co-spinner lines, they are acted upon by the Z2. So they are not gauge invariant anymore, as Z2 is now part of the gauge group. So they do not survive in the pin plus theory. But notice that if I take the direct sum of the spinner and co-spinner lines, let me call it a new line D1SC, then this is gauge invariant. So this survives as a line in the pin plus theory. Okay. Moreover, since I added a new Z2 factor to the gauge group, there is a Wilson line that we obtain, a Z2 Wilson line for this gauge group. And let's call it D1 minus. So in total, the simple objects of the one categorical symmetry of the pin plus 4n theory can be described as follows. So we have the identity and we have the vector, because these are gauge invariant, they just survive. And then we have this direct sum D1SC. We have the Wilson line D1 minus. And then we also have D1V minus, which is just the fusion of D1V and D1 minus. So this looks good, but you might ask, what about the fusion of D1 minus with D1SC? Can that give me a new line? And this is a simple computation to show that it does not happen. The D1 minus line can be absorbed by D1SC. And this is an important computation to review because that's how fusion rules are computed. So let's see how this computation works out. So here we are in the spin theory again. We have the spinner and the co-spinner lines, and they are acted upon by the Z2 charge conjugation. This induces an action on the identity local operators living on these lines. So let's call these identity local operators D0S and D0C. So when I look at the direct sum line, I have a 2-dimensional space of local operators. And I can choose a basis given by the sum of these operators and the difference of these operators. The sum is gauge invariant. So it survives as a local operator in the pin plus theory. And it can be recognized as the identity local operator living on this line. While the difference obtains a sign under the Z2 action. So it lives in a non-trivial Z2 representation and is not gauge invariant. But you can make it gauge invariant if you attach it to Wilson line living in this representation, which is this D1 minus line. So what this local operator tells you now in pin plus theory is that D1 minus can be absorbed by D1 SC, which is what we wanted to show. And then similarly, you can compute fusion rules in this similar fashion. You just go around seeing what representations of local operators there are. And whenever you find a non-trivial representation under Z2, you just attach a Wilson line there. And in the end, the non-trivial fusion rules turn out to be these ones. And then you can recognize them to be Tambara-Yamagami fusion rules based on Z2 times Z2. What this means is that there is an invertible part of the one category controlled by the Z2 times Z2 group. And there is a non-trivial, there's a non-invertible element, D1SC, whose square gives me all the Z2 times Z2 elements. Okay, now you might ask, what is the fusion one category whose fusion ring is this Tambara-Yamagami ring? And it's known that there can be multiple choices of such fusion one categories. So the task is to determine which one it is. There is still some information that we have not determined yet. And this information is encoded in the associator of this category. So this associator can again be determined in the similar fashion like we determined objects, the morphisms and the fusion rules. You start from the spin 4n theory where the associator is trivial, and you just simply go through with the same computation, adding some of the Wilson lines D1 minus in the process. And after doing the computation, you realize that the fusion one category is actually the category of representations of D8, where D8 is the dihedral group of order 8. So this is a non-trivial result because we could have also find, for example, a representation category of the quaternionic group, which also has the same fusion rules. But now there is a nice physical interpretation which tells you that this fusion one category actually has to be rep D8 without doing any associator computations. So to see that, let's go back to the spin 4n theory and gauge Z2 times Z2 one form symmetry instead of gauging the Z2 charge conjugation 0 form symmetry. When we do that, we obtain a 3-dimensional theory with gauge group PS of 4n. So we basically remove the Z2 times Z2 center from the spin gauge group. And after gauging one form symmetry, we obtain Z2 times Z2 0 form symmetry, which is acted upon by the Z2 charge conjugation 0 form symmetry. So the total group is this semi-direct product, which can be recognized as the dihedral group. Now, when you want to go back to the pin plus theory, you want to gauge this dual 0 form symmetry. And you also want to gauge the charge conjugation as before. So you're gauging the full D8. And when you do that, you obtain Wilson lines for D8, which precisely form this one category rep D8. Okay, so this example that I described can be generalized. And there is a whole theory of equivalentizing one category. This is well known in the math literature and also in the condensed matter literature. So our set of, we now start with a one category C, which is the category of symmetries of some D-dimensional quantum field theory. So it describes topological lines and local operators in a D-dimensional theory. And then we have a finite group G acting on this category C. This is the group of 0 form symmetries of this theory. And now we want to gauge G. After gauging G, we obtain another D-dimensional quantum field theory. And the question is, what is the one category describing the topological lines and local operators in this theory, in the gauged theory? And the category is what we will call as the G equivalentization, CG of this category C. And it's built as follows. So the objects of CG are built from two different kinds of objects. On one hand, we have G invariant objects in the original category C. So physically, these are just topological lines which are gauge invariant. So they survived under the gauging process. And on the other hand, we have G Wilson lines, which are objects of a different one category, which is the category of representations of G. And now there is a very nice physical picture over here. which is important because it will feature a lot in the examples, in the generalizations later on when we discuss equivalentization of higher categories. And the physical picture is that you can think of these G Wilson lines as one-dimensional TQFTs with G global symmetry. It's easy to justify this. So 1D TQFTs are just vector spaces. And if you want a G global symmetry, the vector space needs to form a representation of G. But now you might be puzzled. Why are 1D TQFTs becoming line defects in the theory obtained after gauging? And there is a neat physical explanation for that. So on the left, we have our original D-dimensional theory, which has G symmetry, shown over here as a black box. And then we can take a one-dimensional TQFT, which also has G symmetry, shown over here as a red line. And these two are two decoupled systems, not talking to each other. Let me just submerge this 1D TQFT, the locus of this inside the locus of the D-dimensional theory. They don't talk to each other. But then when I do the G gauging, I can gauge a diagonal G. So I can perform the G gauging such that it gauges everything in the bulk, but also simultaneously gauges the G symmetry on this one-dimensional TQFT. So this gauging procedure glues this 1D TQFT on top of your theory, and this TQFT then becomes a topological line defect interacting with the bulk in the theory obtained after gauging. Okay, so in this way we can continue. We can talk about how to construct morphisms of CG. And they're again built from two kinds of morphisms. So on one hand, we have morphisms of the original category organized according to the representations of G. So physically, we take some local operators and they might form some representations in G. And then these morphisms become new morphisms in CG as follows. So here is a picture of what is going on. Take L1 and L2 are two line defects in the theory before gauging, and there are some line changing local operators which form some representation R under G. And when we do G gauging, since these are not gauge invariant, we need to attach them to a Wilson line in representation R. So before gauging, there were morphisms from L1 to L2. But now there are morphisms from L1 to L2 tensor R. But all of this can be tracked. So there is a systematic way of going from morphisms of C to morphisms of CG. And then you also need to include morphisms of this new category that you added, RepG. And this can be physically understood as some zero-dimensional G invariant topological interfaces living between two 1D TQFTs having G symmetry. Okay. So we saw this familiar procedure of G equivariantization for one categories and phrased in a more physical language. One advantage of this is that now we can generalize this construction to equivariantization of two categories. I will sketch again the ideas, but the details will appear in a soon to appear work with Sakura Shiffer-Nameki and Jingxiang Wu. So now our physical problem has a two category C, which describes symmetries of some D-dimensional quantum field theory. So this two category describes topological surfaces, lines, and local operators in the theory. And then there is also zero form symmetry, G, which acts on this two category. And we want to look at the theory obtained after gauging this G zero form symmetry. And the question is, what are the topological surfaces, lines, and local operators in the theory obtained after gauging? What is the two category describing them? And we will call this as the G equivariantization CG of this two category C. So this problem has been considered in the math literature for two categories, but not for fusion two categories. Okay, so the construction is again very similar. First of all, let's look at objects of this two category CG. They are constructed from two kinds of objects. First, you have G invariant objects in the original category. These are simply gauge invariant topological surfaces. and they just survive the gauging process. And then you add objects of another 2 category known as 2rep-G. This is the category of module categories of vec-G, where vec-G is the one category of G-graded vector spaces. There is a nice physical interpretation, which is that these are simply 2D TQFTs with G symmetry. And the reason why these become objects of CG is again very simple, is the same idea. We have a D-dimensional theory with G symmetry. We take a 2D TQFT with G symmetry and submerge it, and then we do the diagonal G gauging. And after doing the diagonal G gauging, this 2D TQFT gets pasted on top of your theory. It starts interacting with it, and it becomes a topological surface defect of the theory, of the gauge theory. Again, one morphisms again can be obtained by combining 2 kinds of one morphisms. So we take one morphisms of the original category, organize them according to how G acts on them, and then they might get modified. How does the modification look like? So here is a cartoon for that. Here's an example for that kind of situation. Take a line defect L before gauging the G symmetry. Now, after gauging, it might get attached to a surface operator living in the 2rep-G part of the 2 category CG. And a simple example to keep in mind why this can happen is that assume that L is G invariant. Then you obtain a zero form symmetry from the G action, a zero form symmetry living on this line. But the zero form symmetry might have a 't Hooft anomaly. So if it has 't Hooft anomaly, when you do gauging, to keep it this line gauge invariant, you need to attach a 2D SPT phase while you perform the gauging. And this 2D SPT phase is going to be the surface defect that it gets attached to. Okay, so there is a well-defined procedure to go from one morphisms of C to one morphisms of CG. And then on the other hand, you need to also consider one morphisms in this new category, 2 category 2rep-G. Physically, these are G-symmetric topological interfaces between 2D TQFTs with G symmetry. And then again, 2 morphisms of CG are obtained from 2 kinds of 2 morphisms. First are 2 morphisms of the category C, organized according to representations, and then 2 morphisms of 2rep-G. So all of this is a little bit too much to digest. Let's see how this procedure actually plays out in a simple example. So we consider a similar theory as before. And again, let me point out that we will go from a 2 category describing invertible symmetries to a 2 category describing non-invertible symmetries in this process. So we again take a pure gauge theory with gauge group spin 4n, but now instead in four dimensions rather than 3 dimensions. So the one form symmetry Z2 times Z2 now describes topological surface operators. So it describes a simple 2 category. The objects are now D2 as D2C, D2V. And then let me also define D1s with the same SCV labels, which are simply identity lines living on these surfaces. So in the categorical language, they are one endomorphisms of these simple objects. And so there's again the zero form outer automorphism symmetry, which exchanges S and C labels for both surfaces and lines. And now we want to gauge this Z2 charge conjugation symmetry and go to the pin plus 4n theory in 4 dimensions and ask what is the 2 category formed by topological surfaces, lines, and local operators in this theory. So first, to determine the surfaces, we need to look for 2D TQFTs which have Z2 symmetry. And there is a single non-trivial answer given by Z2 gauge theory. So we can write down what are the objects for this 2 category associated to pin plus theory. We have the identity surface and the V surface, they're gauge invariant. Then we have the direct sum of the spinor and co-spinor surfaces, D2SC. We have the Z2 gauge theory surface, D2Z2. And finally, we can take the fusion of D2V and D2Z2 to obtain a new surface, D2VZ2. So let me say a few more words about what this new surface D2Z2 is. This is also known as a condensation defect. And this has been discussed a lot in the literature recently. So how this is obtained is that you take the Wilson line that you had that was generating a 2-form symmetry in the theory, not a 1-form, that's a typo. And then you gauge the Z2 2-form symmetry on a surface rather than in the whole theory. That produces for your condensation a surface defect. And this is precisely this D2Z2 that we discovered. Okay, so far everything looks like in the case of 3 dimensions with the map that D1 minus and D2Z2 are on the same footing. But let me point out that they are not on the same footing. And the difference arises when you take fusion rules of these guys. So recall that D1 minus was an invertible line. It was following Z2 fusion rules. But D2Z2 is not invertible. If you square it, you get 2 times the surface. So it's a non-invertible surface. And moreover, there is no way for you to escape having this D2Z2. So if you care about all the surfaces that are coming from the spin theory and you want to incorporate them, then you must definitely have this D2Z2 surface in your category, because it arises in this fusion rule. If you take the SC surface and fuse it with itself, you get the Z2 gauge theory condensation defect and its V analog. And this provides with us to us a non-invertible fusion rule at the level of surfaces in this 2 category. Okay, let me skip now to 1 level up and discuss equivalentization of 3 category. So mathematically, we can follow the same procedure. Start with some 3 category C with a G action on it. And you want to equivalentize it to get a new category C, 3 category CG. Again, you will make objects and morphisms of CG out of objects and morphisms of C, which are G invariant, and objects and morphisms of an additional 3 category, 3rep G, which we can define to be the category of modules of 2-vec G, where 2-vec G is the 2 category of G graded 2 vector spaces. So this might be consistent. This might give us a fine definition of CG. However, here's the physical problem and this mathematical construction do not quite match at the level of 3 categories. The physical problem was that we are gauging this G zero-form symmetry, and we want to describe all the possible 3 surfaces, 2 surfaces, lines, and operators that can be obtained. But these 3rep G does not capture all those possible 3-dimensional topological defects that we can obtain after gauging G. It only captures a subset of them. And this is because there are more G-symmetric 3D TQFTs than the ones captured by this 3 category 3rep G. So in a sense, the G-symmetric 3D TQFTs that this 3 category captures are just those for which the underlying 3D TQFT, does not carry any topological order. So for lower categories, this was fine because there was no topological order. So 2rep G and rep G give the correct, the full physical answer. So this suggests that from 3 category onwards, there should be an extension of equivalentization procedure, which gives the full physical answer. Okay, so now let me discuss some examples of higher categorical symmetries, some physically interesting examples. So, well, they're easy to construct. All you need is a 0-form symmetry acting on higher form symmetries. And there are many interesting examples in diverse dimensions that you can consider. So for example, in 5 dimensions, one can consider maximally supersymmetric Yang-Mills theory, which has a UV completion as a 60 2,0 SCFT compactified on a circle. And you can, for example, look at the super Yang-Mills theory with spin 4 and gauge group, and gauge its outer automorphism, which acts on the one-form symmetry. So after gauging, you would obtain a non-invertible three-categorical symmetry. Now, in 6 dimensions, one can consider 2, 0 superconformal field theories, which have two-form symmetries. So there is a 2, 0 SCFT of type SO4N, which has Z2 two-form symmetry. And one can take 2 copies of this theory. And then there is an exchange symmetry, which exchanges the 2Z2 two-form symmetries. And one can gauge this exchange symmetry. After gauging, one would obtain a non-invertible three-categorical symmetry. Coming back to 4D again, n equals to 3 theories should have non-invertible two-categorical symmetries because they're obtained by gauging S duality of n equals to 4 super Yang-Mills theories. And S duality acts non-trivially on the one-form symmetry of n equals to 4 theories. So let me conclude. What we are witnessing is the beginning of a new symbiotic relationship between quantum field theory and higher category theory. And I should stress here that these are non-topological quantum field theories. In the context of topological quantum field theories, it's already very well known that they are deeply related to higher category theory. But here we are making a connection to non-topological QFTs. And the relationship is made by studying symmetries of these quantum field theories. And this relationship goes both ways. So on one hand, physical properties of non-invertible symmetries in QFT are conveniently encoded in the structure of a higher category. And so the study of these symmetries is a natural place for applications of concepts of higher category theory. And on the other hand, there are various intuitive ideas that people use in this physical context of studying quantum field theory. And these physical ideas can spur new developments in higher category theory. We discussed examples in this talk, like equivalentization procedure, and the prediction that there should be a generalization of this equivalentization procedure. And since we have these concrete physical applications of higher category theory, it provides some motivation to explore higher category theory even further. That is not just some abstract nonsense. You can compute explicit quantities out of it, which are important for physical systems. So let me finish with some future directions. In this talk, we considered equivariantization processes. One can also consider opposite processes, which are known as de-equivariantization or condensation. In the context of quantum field theory, these would be called as gauging of higher form symmetries rather than zero form symmetries. And then what one can do is that start from a higher category and do some equivariantization and de-equivariantization to produce new higher categories. And in this way, one can construct a web of higher categories, which closes upon itself. And this web describes symmetry categories for a web of theories related to each other by gauging and ungauging higher form symmetries. So this is an interesting structure that comes out. Then you have another natural question is to ask, how do these higher categorical symmetries act on generically non-topological defect operators in the theory? So one of the ways to characterize zero form symmetries is to describe their action on local operators in the theory. And a way to characterize higher form symmetries is to describe how various extended operators in the theory are charged under these symmetries. So there should be a similar characterization of higher categorical symmetries in terms of some categorical action on extended and local operators in the theory, the full spectrum of extended and local operators, including topological and non-topological ones. And this is only, we have only begun to scratch scratch the surface of the subject. There's lots more to do, especially in the context of physical applications of these higher categorical symmetries. And I invite you to join this exciting field. Thank you very much.
There's a very nice non-topological two-dimensional field, namely the two-dimensional sigma model. You can take the Versumino-Witten sigma model. It has to have the Versumino term, which is defined, to which you can associate, in the presence of defects, a bicategory, a weak two category, naturally. And that's the bicategory of gerbs on the, roughly speaking, on the target space of the sigma model. And I just wanted to point out that this equivariantization procedure, as a valid substitute for the minimal coupling recipe, in the presence of non-invariant tensors defining in the background of the sigma model, or worse still, proper gerbs, not just non-invariant tensors, non-invariant under the rigid symmetry group, has been worked out by Walldorf, by Gawęcki, like Professor Gawęcki, Walldorf, and myself in 2012. And there you actually see that equivariantization introduces Wilson line associated with symmetries that you gauge in the worldsheet orbifold picture. And you can actually even see non-invertible symmetries. These go back to, again, Gawęcki, 2005. He found, precisely studying this orbifold, spin 4n by Z2 cross Z2, he found so-called non-abelian branes in the Versumino-Witten model. And if you sort of fuse, if you fuse the branes with the multiplicative structure on the gerb, which always exists, and do the gauging, you obtain non-invertible symmetry defects. So this is a huge playground which you might find useful. There's a bicategory, and there is equivariantization, non-invertible symmetry defects. So, well.
Thank you very much for the comment. Yeah.
So, any more questions?
What is the relation with Professor Fried talk? I think that mathematically it is very similar things happening.
So in Dan Fried's talk, one was studying TQFTs in one dimension higher. So one was taking these QFTs and realizing them as interval compactification of one higher dimensional TQFT, with one boundary condition being non-topological and the other being topological. And this interval compactification was this non-topological quantum field theories that we are studying.
But you were very liberally gauging this R-form symmetries left and right, right? So, yeah, so you're quite liberally gauging this higher form symmetries, and that could potentially cause anomalies. So I assume you're very careful that what you're doing when you're gauging this higher form symmetries, you have non-anomalous field theories.
Right, so that's why I looked at pure gauge theory without any matter content. So there can be anomalies.
That's how, okay, so that was the
yes, but in this slide over here, in this slide, there are supersymmetric theories everywhere, and they can have anomalies, and we are investigating that issue. Yes.
Right, and it's also related to swampland program.
I see.
So, any other questions? So, in your two categories, so case, surface operators can carry only discrete abelian charges, right? Not the non-abelian.
Depends on how what's the dimension of space-time. So, in 3 dimensions, they can be non-commutative.
Right, but higher dimension.
Yeah, there needs to be a commutative fusion rule.
Right. Okay. Any more? Otherwise, thank you.
Okay. Thank you.